Hello and welcome to Chapter 3, more specifically Chapter 3.1 from Stevens's Matrices, Vectors, and 3D Math. Right? And so as we get into this chapter we're talking about vector-valued functions. And the point I'd like to make is that we've actually already seen one of these. So I'm going to take us back to Chapter 2.5 for just 1 second. And when you look at the parametric equations for a line, we said that they look like this. There's actually 3 equations. There's the equation for x, there's the equation for y, and there's the equation for z, and they're all functions of some parameter t. Right? And this, as the parameter goes over some domain, in this case in the formal definition negative infinity to infinity, it sketches out a line in 3 space. So this is actually a vector valued function. Check, we've seen one. Right? To put it in formal notation, a 2-dimensional vector valued function basically has an x function and a y function, and if you put them in the little brackets, you're creating a vector. So what you're really doing is, if you think about 2D, you have this vector and it terminates at a point that we'll call x of t, y of t at some given value of t, and that might move around through 2 space or 3 space for that matter. And 3 space, there's an x, a y, and a z, just like our line in 3D that we just saw in Chapter 2.5. And so when we get into 3.1, we're just going to talk about these, and later we'll do some differentiation of these curves. But for right now, we'll just talk about vector-valued functions and just give some examples. And so again, just to reiterate, I basically have one parameter t and then 2 or 3 functions of that parameter. 2 if I'm in 2 space, 3 if I'm in 3 space. So let's see some examples. And we've actually seen a couple of examples already. When we did our ellipses, we created this vector-valued function, only we said something like x equals 4 cos t and y equals maybe 2 sine t. And that gave us this ellipse that was sketched out around like this for t going from 0 to 2 pi. Right? Notice it has a x radius of 1, 2, 3, 4, and a y radius of 1, 2. Right? And so we've already done this. We've called these parametric equations, but you stick them in a little triangular brackets there, you've got a vector-valued function. Right? Let's take a look at another one. This is a rose, right? And you can get some sort of interesting like spirograph type graphs whenever you play around with this. So here's x of t, right? X of t, and here is y of t. And if you look at this, part of this is a cos t for x and sine t for y. If this function was just a 1 and this was just a 1, we'd be tracing out a circle, right? It would be over here, it would be a unit circle looking like that, right? T going from 0 to 2 pi. But it's not doing that because the radius is not constant. The radius, it is a radius because there's the same coefficient in front of cosine t as there is in front of sine t. Right, so you can sort of think of this as a circle being traced out as t goes from 0 to 2 pi, except the radius looks like this. We'll do the radius over here on the left. For t, the radius, because that's sine 2t, looks like this. It starts at 0. I actually get 2 sine waves. So the radius goes up, down to negative, up to positive, down to negative, up to 0. So when you come over here, and it's not immediately obvious if you looked at this thing how it was sketched out, you wouldn't be able to tell. But you first start there because and keep in mind, as theta goes from, or as t goes from 0 to 2 pi, not theta, I'm going around this circle, or around the positive x-axis in the counterclockwise position, starting at the positive x-axis. So initially my radius is 0, but then I start continuing, my radius gets bigger and bigger, and then it starts heading back down to 0 again. And now as I head over into this part of my domain for t, the pi over 2 to pi, the radius suddenly becomes negative. And so I'm actually down here. It's getting negative big, then it's negative 1, then it gets negative and smaller. All right, and that brings me back to the origin again. And as I'm down here, all right, now my sign is positive again. I'm up here in the sign portion. So I'm down here going positive, getting bigger, and then back down to 0, and then finally, as t finishes up from 3 pi over 2 to 2 pi, it comes around here. I now have a negative radius, and I get this nice little flower-shaped curve. All right, and it takes a little while to sort of visualize that, and you shouldn't be afraid to just grab the code and play with it. Change some parameters. Right? So you just first set your t. Here I have 0 to 2 pi, and I have 300 points. And here's x, there's y, and then I just do plot xy with some graphics directives there. So, don't be afraid to play around with these portions of the radius. Here they're the same. You can switch them up, change the coefficients of t, things like that. So go grab the file rows.m from the chapter 3 repository. Pull it up, run it, and then play around and change it and see what that does to your graph. So now if we do the same thing in 3D, here's an example. We call it R in this case instead of V. There's my x value is cos t, y is sine t. If you notice that if we were just in 2 space, this would sketch out the unit circle. Right? And then this is z, that's just growing as t gets bigger. So as t goes from 0 to 6 pi, I'm going to trace out that circle once, twice, 3 times. But while that's happening, z is going to increase. So there I'm going once, twice, 3 times, and z is going up like t. Right? So that gives you my helix. And again, you might want to go grab the code helix.m from the Chapter 3 repository, play around with that. And you can, there's the coefficients, there's the x, y, and z. You can change the, I guess this is the radius of our circle to be functions of t again, and see how that plays out in 3 space. What's another one? Oh, twister. Okay. So, that's this example here. So if you look at this x and y, so when you look at the x and y component, all right, what we have, so this is t cos t for x, y is t sine t. It's going to trace out a circle, right? Only the radius, which are these coefficients, is growing like t. So the radius starts at 0 and grows out. Right? So that's doing a spiral in 2D. But my z component is just getting bigger. So as t increases from 0 to 20 pi, z just goes up like t. Right? So if you're to pull this code, there isn't one. What you have to do is play around with helix here and adjust it to look like this one. All right. All right, so you should go in here and change this to a t. Change the 5s to t. And when you rotate it around, and if you can look straight down into the twister just by turning it your direction, you'll see that what we have is just this curve that spirals outward from the origin in the counterclockwise position. And so that's just an example of different functions you can create. They're curves in 3 space. Right, they're one-dimensional curves in 2D or 3D. It's a great way to move around in 3D. It sort of expands your world of graphing dramatically. But you might say, hey, I don't want to lose the good old y equals f of x. I say I'm comfortable with y equals f of x. I don't want that to go away. And what this last page here tells us is that it's actually really quite easy. If you like y equals f of x, you can create the vector valued function for that very simply. Right, so if you have some function y equals f of x, right, then you just create, and x is on some domain, then you just create the vector valued function where x is t and y is f of t. Right? And that's going to sketch out the exact same curve. For example, if I wanted to sketch out y equals negative x squared plus x plus 6, and that's just a parabola over x going from negative 2 to 3, I would just have this vector valued function. Again, there's x, it equals t, straight up easy to do. There's y, it's just what the role that x plays, and y equals f of x. And then your domain on t is the same as the domain on x was. Alright, so it's easy to do. Your y equals f of x is not gone away. You can still graph these the same way. I mean, you could even still do the y equals f of x. But parametric curves just allow you a little bit more freedom both in 2D and 3D. Right? It allows you to draw specifically, if you do y equals f of x, you're restricted to graphing functions. Whereas if you do x is a function of t, g of t, say, and y equals h of t, you can graph things that aren't functions. Right? For example, that is not a function. If this is x, y, it's not a function. It fails the vertical line test, but it's easy to graph parametrically. Right? You don't need the y as a direct function of x. So that's 3.1. 3.2, we'll get around to differentiating these things, and I will see you then.